thought it would be better if I would take the class on its scheduled day. That is the last working day of the semester. Anyway, actually, still I am not in good condition. So let us make it very quick. And for today's class, we actually have two objectives. One is we started one chapter, hypothesis testing, that you can see on my screen. We like to finish it. It's a big chapter. So we will finish it as quickly as we can. And also, I like to discuss, the CR also requested yesterday. Okay, what I like to discuss about the syllabus. Usually, I do not actually discuss about the syllabus. Whatever is covered usually are the part of the syllabus. But this time, I think syllabus is a bit big. Especially the syllabus is imbalanced in the sense the syllabus before the mid and after the mid are not equal. That's why syllabus, if you consider it for the mid exam, it was a bit very short, but for the final, it is a bit long. So we need to make a balance. Okay. Before going there, let us first review about hypothesis testing. I think we had a class on hypothesis testing. Please respond. Otherwise, it would be very difficult for me to actually even understand whether you are with me or not. So in case of hypothesis testing, we define hypothesis in that class, and we define it as a statement it's a statement which can be true or false, and usually is related to a population parameter. Also, it can be related to the population distribution. We can have a hypothesis testing related to the population distribution, but in this course, we will not be covering that one. So it will be related to a population parameter. And usually, here we will have the mean or variance. And purpose of this testing or hypothesis testing is to statistically decide statistical decision related to whether you reject the hypothesis or you fail to reject hypothesis. We usually do not say we accept the hypothesis. Instead, we say we fail to reject the hypothesis. And in defining a hypothesis, actually, we have two options. Actually, we need to define the actual statement that we want to actually prove is defined as the null hypothesis. We denote it by H naught. And usually our goal is to reject the hypothesis, not accept the hypothesis. Our goal is to reject the hypothesis. And another one is alternative hypothesis or alternate hypothesis that we denote by H1. It actually is a complement of H naught, usually. This means if we reject H naught, the null hypothesis, then actually we accept the alternate hypothesis. On the other hand, if we do not reject the null hypothesis, then actually we reject the alternate hypothesis. So here actually our goal is in hypothesis testing, if we actually conclude here, we need to first identify the parameter related to the testing. And once we have identified the parameter related to the testing, then we need to define the null hypothesis and the alternate hypothesis. Once we do these two tasks, actually, then we need to collect a sample or random sample. Collect sample. From the sample, actually, we need to define a statistic as we define a statistic is a function of the random variable in a random sample. This statistic is defined so that it is related to the parameter, or more specifically, it is the MLE of the parameter. So if we consider that mean is the parameter for which we are actually going to test the hypothesis, then the statistic will be the sample mean X bar, which is this one. On the other hand, if we assume that it is the variance of the population, then actually we define the sample mean, sample variance as S squared, which is summation for all values xi minus x bar squared divided by n minus 1. So we actually define a statistic that actually is related to the parameter for which we are going to test the hypothesis, and it actually is the MLE of the MLE means maximum likelihood estimator of the parameter. Now, once we have the statistics, then we need to know the distribution. This is very much important. Distribution of X bar or S squared. Once we know the distribution of X bar, then actually we can take the statistical decision. How? Actually, the statistical decision is taken, as we discussed in the first class, there are three things based on which we actually take the statistical decision. Either we have a critical value, we have a critical point, or critical region, or we defined a significance level, or we defined the p-value. All these three terms actually have been defined in the last class. Usually, we will not define the critical points explicitly. Instead, either we'll go for the significance level alpha, or we will directly identify the p-value. In defining the significance level, actually, most of the cases we define significance level alpha either as 0.05 level of significance or 0.10 level of significance. This means that alpha actually is the significance level. On the other hand, it's the probability of the type 1 error, that is probability of rejecting a true null hypothesis. That means even though the null hypothesis is true, this one S1 is true, the sample mean could have a value which is in the critical region and with probability 0.05, we will have to reject the null hypothesis. So either we'll go by the critical points or significance level of the test, it will be given, or you will be asked to calculate the p-value. If neither of these two are mentioned, then actually it is customary to assume that you will test the hypothesis with a certain alpha level, and you will assume the alpha level either 0.05 or 0.10. It is your own choice. So once we can take the decision whether actually it will be based on significance level or it will be based on p-value, then actually we take the decision that whether we reject the hypothesis or we fail to reject the hypothesis. And to take this decision, actually, we need to define a quantity. We call it test statistic. This test statistic actually is defined based on the distribution of the parameters. Why? If you know the distribution of the parameter, for example, if we are going for testing the mean of a population, then if we know that X bar is normally distributed and an alpha level is given, then actually it is very easy. We know X bar is normally distributed and alpha actually is 0.05, then actually finding the critical points are very simple. We need to leave a space here, which is alpha by 2, leave a space here, which is alpha by 2. So this point becomes Z alpha by 2, and this point becomes Z alpha by 2. This is 0. So this is the standard normal curve. And what we need, that the sample mean that we have estimated by MLE is within this interval from minus Z alpha by 2 to Z alpha by 2. And to test this one, usually what happens, if we draw this line, if we have the X bar here, the X bar actually is, in case of critical points, we define one critical point, this is upper critical point, this is lower critical point. If X bar is within the critical point, we do not reject it. On the other hand, if X bar is here or here, we actually reject the null hypothesis. And in that case, actually, we need to define the critical points. Actually, it is usually mu. So we will not use this one. Rather, we will go for the test with a given significance level either, or we will directly calculate the p-value. What we do here is, actually, since we have the distribution of the parameter X bar or S square, what we need to do, we need to actually convert X bar into a standard normal form. And then the test statistic is defined as X bar minus mu divided by sigma divided by square root of n, given that X bar is normal with parameter mu and sigma squared divided by n. And we call this as the test statistics if X bar is normal and we know the variance. So variance is known. We will see the different cases where actually the distribution will vary. But for now, once you have the test statistics, now we need to compare whether this test statistics is within this interval or it is outside. That means here or here. If it is within this interval, then we do not reject the null hypothesis. If it is outside this interval, then actually we reject the null hypothesis. This is the case here. And second thing is that for different, as you know, a different value of alpha, for example, when alpha equal to 0.10, then actually Z alpha by 2 will be here. And actually the test result will change. Here comes the p-value. P-value actually is a generalization of the significance level. Instead of testing the hypothesis based on a certain significance level, p-value actually finds the minimum significance level at which the null hypothesis is rejected. Any significance level lower than this, the null hypothesis will not be rejected. Any significance level higher than this, the null hypothesis will be rejected. So without further delay, let us move into an example, and with that example, we will cover all of these stuffs. Here, The example is actually known to us. The example is that we are sending a signal from a location A to a location B. It is known that the signal that is sent from location A is with amplitude mu, and on the way actually a noise N is introduced which has a normal distribution with 0 mean and 4 variance. So the received signal here is mu plus N. And it is actually claimed that on a given day, the signal is sent with amplitude mu equal to 8. Now you need to actually test the hypothesis that mu is equal to 8. This is now, and you will test it from the received signal. So if you consider only the received signal, then the received signal mu plus N actually has the distribution normal with parameter always. Actually, since the noise has 0 mean, so the mean of the sum will remain mu, and the variance will be variance of the noise. This one. Now we want to test whether the signal that is sent on a given day has the amplitude 8 or not. To do so, what we do, we receive 5 signals. So N equal to 5. This N actually is overlapping here, right? Okay. Okay. Okay, let me write it noise. So N equal to 5, and the sample mean of the 5 measured signal is found to be 9.5. And not to mention that the received signal is normal. So X bar is normal, not approximately normal by CLT. It is normal because it is the average of 5 normal signals. Now, in doing the hypothesis testing, we need to go step by step. The first thing, you need to identify the parameter related to the testing. Which is mean mu. And then actually you need to define the hypothesis. The hypothesis is the null hypothesis, which is mu equal to 8, and alternate hypothesis, which is mu not equal to 8. It's a two-sided test. We'll see one-sided test later on. Now, number 2, the sampling statistics that we defined here is the MLE by X bar, and which is I equal to 1 to 5 xi divided by 5. And we found that it is 9.5. Since no significance level is given for this test, we assume that the significance level alpha is equal to 0.05. Mind it, whenever it is not given, and if you are asked to conduct a hypothesis testing, you can assume any values. So what is the next step is to find out the test statistics. The test statistic is to standardize the sample mean, which is X bar minus mu sigma divided by square root of N, which actually is X bar equals to 9.5. The mu actually is the value when the null hypothesis is true, which is 8. Sigma has a value 2, and N has a value 5. Then what we have is, following the text, we can see it is 1.68. So our next goal is to take the decision related to the test. Okay. since alpha is equal to 0.05, so we know Z alpha by 2 will be Z 0.025, which is following the table of the normal distribution 1.96. And if you just draw the normal curve, then you will find here 1.96, one of the critical value. Another one is minus 1.96. And since it is standard normal, it is 0. And we found that the measured value of the test statistic is right here, 1.68 within the acceptance region. So we take the decision that since TS, absolute value of TS is less than Z alpha by 2, that is 1.68 is greater than minus 1.96 and less than plus 1.96. So we say we fail to reject the null hypothesis H0. So this is our decision. So whenever you will conduct a hypothesis testing, you need to conclude whether you reject the null hypothesis or you do not reject the null hypothesis or you do not reject the null hypothesis. Just for an example, if we assume that alpha equal to 0.10, then Z alpha by 2 will be Z 0.05, which is 1.65 from the table of normal distribution. Then we find that the value of the test statistic is less than 1.65. Less than? No. TS is greater than 1.65. So we reject the null hypothesis. Is this clear? Actually, anybody is hearing me?
Yes, sir.
Yes, sir.
So are we understanding?
Yes, sir.
Yes, sir.
So the main thing related to the test is that here actually the variance is known. Can anyone tell me if the variance is not known, what problem will we face? Anyone?
Then we have to deal with the population sample variance, and it will have t distribution.
Very good. Actually, if we do not know the variance, then here actually the test statistic cannot be calculated because calculation of the test statistic require the value of sigma. And if we do not know the value of sigma under that, we actually calculate the sample variance, and then actually x bar minus mu s by square root of n, it does not have the normal distribution. So the whole test will be different, and we'll deal with that later. So for now, we are considering a hypothesis testing for, so our goal here is hypothesis testing for the parameter mean from normal population and we know the value of sigma squared. So under this circumstance, actually we identified that parameter is mu. We defined the null hypothesis. Actually, my previous experience says many of these students actually cannot even define the null hypothesis and alternate hypothesis. One thing that you must have to remember that these two are complementary. So whenever the null hypothesis is true, the alternate hypothesis cannot be true. Usual case this is. So if you do, so here in this case, we want to actually claim a certain value of the parameter mean. Mu is equal to 100, mu is equal to 200, mu is equal to 300. And we want to, if the null hypothesis is not true, then actually the value of mu will not be equal to 8. It will be other than 8. In that case, we actually have the null alternate hypothesis which says mu not equal to 8. And then we need to calculate the value of the sampling statistic X bar. In this case, it was given that after receiving 5 signal, it is found that the sample mean is 9.5. But you might have a problem where instead of giving the value of the sample mean, you are given 5 values, 10 values. So what you need to do, you need to calculate the sample mean. Once you have the sample mean, you need to find whether the value of alpha is given or not. If it is not given, then actually you need to assume a value of alpha 0.05 or 0.10, and then you need to calculate the test statistic. By the term test statistic, actually we want to standardize the value of the sample mean so that we can compare it here. This one actually is alpha by 2. This one is alpha by 2. When alpha is 0.05, then we know it is 1.96. So the critical values actually are directly found from the standard normal distribution probabilities. And then our goal is to just, by the test statistic, our goal is to convert this X bar into its standard form. So here actually we test the null hypothesis based on 2 different significance levels. Now, what is p-value? P-value actually is the minimum significance level at which we reject the null hypothesis. Any significance level lower than this, we do not reject the null hypothesis. How it is called? Whenever actually you have the test statistic right here, TS, then actually just consider the scenario here in the left-hand side figure. We compare this TS with the critical value that is defined from alpha, or more specifically, alpha by 2. So, as long as this region is here, let me draw it by green lines. So this is one value of alpha, this is one value of alpha, this is one value of alpha. For all these 3 values of alpha, let's say this is alpha 1, this is alpha 2 by 2, this is alpha 1 by 2, this is alpha 3 by 2. All of these cases actually, these values here actually are larger than TS, and we do not reject the null hypothesis. On the other hand, as soon as the value of alpha is chosen in such a way so that this Z alpha by 2 will be smaller than TS, we will reject the null hypothesis. Even when actually it will be right here, we will reject. So, when we test the hypothesis in terms of a significance level, the significance level gives us the critical value. We compare it with the test statistic. On the other hand, when we go by the p-value, instead of considering any specific significance level, what we do, we actually consider the minimum significance level at which we need to reject the null hypothesis. Any significance level higher than this, that means in this side, we reject the null hypothesis. Any significance level that is smaller than this, we actually do not reject the null hypothesis. So this is the minimum significance level. For example, if we assume that this produces n alpha by 2 equal to point, say, it is 0.05. This is 0.10. 0.10, we reject the null hypothesis, and say 0.09, not alpha by 2. This one actually is 0.09. So alpha by 2 is equal to 0.045 or 46, whatever. In that case, actually, what happens? If our significance level is less than this, which occurs in case of 0.05, we do not reject the null hypothesis. If it is higher than this, that means 0.10, we reject the null hypothesis. Question is, what actually we calculate by p-value? This significance level actually leave an space here on both sides of the critical value, which is exactly equal to alpha. Here, p-value actually leaves a space on both sides of the normal curve, which is this one and this one. And this actually, so we need to calculate this area. We need to calculate this area. And the sum of these two areas will be the p-value. So it is very easy to know if you know this value, then it is very easy to find out this area. How? This area will be actually, let me mark it. If we subtract this area, this green shaded region from 1, then actually we get the red shaded region. So that means 1 minus phi of the test statistics gives you this area. Let me mark it again by the blue curve. This region is this one, and we have an equal portion here. So p-value is equal to 2 into this. And if we exactly calculate it for a test score equal to 1.68 from the table, where is the table? Let us find the table. Here is the table. 1.68. This is the normal curve. Here actually for 1.68 is 0.953. So it will be 2 into 1.953 or 954, you can say, considering the next digit is 5, then we get it 2 into 0.046, which is equal to 0.092. So whenever we test the hypothesis in terms of a significance level given or assumed, then the test result is actually defined based on Z alpha 2 and test statistics. Z alpha 2 is found from the alpha value. On the other hand, whenever actually we conclude the test based on a p-value, then actually we can tell the result for any alpha value. For example, if your p-value is 0.092, So as long as alpha is less than 0.092, we do not reject the null hypothesis. If alpha is greater than or equal to 0.092, we reject the null hypothesis. So just to remind you again, p-value actually is it is the probability that the standard normal random variable is the absolute value of the standard normal random variable is greater than TS. Or you can say the absolute value of TS. And then we can write the 2 into probability that standard normal random variable Z is greater than the absolute value of TS, which actually is 2 into 1 minus phi of absolute value of TS. Okay. Any question here?
Sir.
Yes. Carry on. Someone was asking a question, right?
No, sir.
Okay. The final thing that is related to the hypothesis testing is the beta. The beta value is calculated based on a particular value of the parameter, and it is defined as the probability of failing to reject a false null hypothesis is not. That means if a null hypothesis is false, that means the null hypothesis that we had considered mu equal to 8, if this one is false, then actually, if we do not reject it, or loosely speaking, if we accept a false null hypothesis, that means an error occurred. We call this error the type 2 error, and it is the probability of a type 2 error is defined by beta. For calculating the value of beta, actually what we need to know the true value of the parameter. We can calculate, we will be able to calculate the probability of type 2 error if and only if the true value of the parameter is given. And this one actually is beta mu1 actually is the probability that your test statistic is less than Z alpha by 2, or it is greater than minus Z alpha. This is very simple. If we just look at here, you are testing a hypothesis and you calculate the test statistics 1.68. And once you have the value of 1.68 for the test statistic for a given significance level, say alpha is equal to 0.05, if you find it is less than 1.96, actually you do not reject the null hypothesis. If the true value of the parameter is 10, for example, instead of 8, then you are accepting a false null hypothesis and you are committing a type 2 error. Beta actually calculate the probability of such an error. And whenever actually your test statistics value will be within this interval, you will accept the false null hypothesis and it will commit the let's say the value of the null hypothesis instead of 8, let's consider it is mu naught to generalize the equation. And it is sigma by square root of n is less than z alpha by 2. The problem is we cannot calculate this probability. Once it is given that okay, let me draw the diagram here. It is 8, but the true value of the parameter mean is mu, which is 10. That means we have a curve like this. So what is the problem here? The problem is we cannot replace this one by z. Why not? Because this mu naught is not the mean value. This mu naught is not the mean value. So we actually cannot replace this x bar minus mu naught divided by the variance by the standard normal random variable. So to do that, what we need to do, we actually need to do a number of things. Let me write it. We can replace it by z if we actually subtract the sample mean by this. If we do this, then actually we need to subtract mu1 by sigma square root of n from the left hand side, as well as we need to subtract this. Do you understand this? Is the move from this equation to this one understandable?
No, sir, if you could repeat it again.
Okay. What I told that this circled quantity is no longer a standard normal random variable. Why? Because the null hypothesis is false. That means mu is not equal to mu naught. That means we write the null hypothesis in that way. Rather, the alternate hypothesis, which is mu equal to mu1, is true. So if mu1 is true, then the sample mean x bar is normally distributed with mean what? Now mu1 and sigma square by n is the variance. However, we test the null hypothesis with a value of mean, which is mu naught. That's why the test statistic produce this one, where mu naught actually is not the true parameter value. The true parameter value is mu1. So okay. I also made a mistake here. That's why what we need to do, we need to subtract mu1 here by sigma divided by square root of n. And actually this mu naught divided by sigma divided by square root of n is separated here. So to subtract mu1 by sigma here, we need to subtract it from the left hand side and from the right hand side as well. That's why this equation becomes this one. Is this clear now, or I need to write it more?
So, sir, left side also we will subtract mu naught.
Okay, let me erase it, right? This middle quantity actually is, first let me write it, x bar minus mu naught divided by sigma divided by square root of n. Here actually, this is not the true mean. What we want x bar minus mu1 divided by sigma divided by square root of n. Then actually we have, okay, this quantity is the standard normal random variable set. So what we need to subtract mu1 here. Subtract mu1. Then if you subtract mu1 here, then actually this one now becomes extra. So the extra quantity will be mu naught divided by sigma divided by square root of n. You understand? This one is equal to this one.
Yes, sir.
Okay. If this is the case, then here actually what we can write here in the middle, x bar minus mu1 divided by sigma divided by square root of n minus mu naught divided by sigma square root of n. And in converting this one into this one, actually, we subtract the middle quantity by what? By a value which is mu1 divided by sigma divided by square root of n. If we subtract this one here, then this becomes this, and eventually we get this. So to make the inequality intact, what we need to do, we need to subtract it from z alpha by 2 minus mu1 divided by sigma. We need to subtract it from the left hand side as well as from the right hand side. Z alpha by 2 minus mu1 divided by sigma square root of n divided by. And in this case, actually, this quantity is z, and we want to actually offload it from here. So we will add this quantity from all sides. Then this becomes probability that if we add it, then it becomes mu naught minus mu1 divided by sigma divided by square root of n minus z alpha by 2 is less than this quantity, who is now is z, is less than mu naught minus mu1 divided by sigma square root of n plus z alpha by 2. Therefore, it is z is less than this and greater than this. We can write it phi of this quantity mu naught minus mu1 divided by sigma square root of n plus z alpha by 2 minus phi of mu naught minus mu1 divided by sigma divided by square root of n minus z alpha by 2. So this is the ultimate value of the probability of type 2 error. Let me write it here fresh. Beta when mu1 is given is the CDF for the value mu naught, that is the false null hypothesis, divided by mu1, the true null hypothesis, this one, plus z alpha by 2 minus mu naught minus mu1 divided by sigma divided by square root of n minus z alpha by 2. So this is one of the critical formula. Don't be worried. It will be given in the question just to show you for the example that we considered just a few minutes back. If we want to determine the probability of accepting the null hypothesis that mu is equal to 8 when the actual value sent was 10, that means the mu not equal to 8 and mu1 equal to 10. That is the true value sent was 10. Now we want to find out the value of the beta. And as we know, the value of the beta is right here that we just derived. Actually, I use the term mu1 here. They use just mu in the text, no problem. So to calculate this, actually, first you need to calculate this quantity. This quantity is calculated here. Mu naught is equal to 8. Mu is equal to 10. Sigma is equal to 2. So this 10 minus 8, 2, this actually is converted into minus 1, and then n is equal to 5. So we have this one, and this results in minus a square root of 5. So the left hand side, this becomes, left part becomes phi of minus 5 plus 1.96, and this becomes minus 5 minus 1.96. And then since this is a negative term, what we can do, we can make it minus phi of, if you take a minus common here, then it will be a square root of 5 minus 1.96. And this will be minus 1 minus phi of a square root of 5 plus 1.96. And then this minus 1 cancel out each other. This will be plus. And what we have is phi of a square root of 5 plus 1.96 minus phi of a square root of 5 minus 1.96. And if we just look at the values here, this becomes 4.196, this becomes 0.276. As you know, phi of this one, actually, this one is 1, and this one is, 0.276, 278. 0.28, 0.57, 0.57.
There is 0.61.
Just a minute. Right. Here, 0.2727. This one here, actually 28. Approximately it is 0.28, 0.61. And actually the value becomes 0.39. Say 1 minus, if it is 1 minus 0.61, it becomes approximately 0.39. So, what we actually see here, that actually when the true value of mu is equal to 10, then the probability is 0.39. That means almost 40% cases actually we accept the false null hypothesis. And a curve actually is shown here. We call it the OC curve, operation characteristics curve. This actually is a function of this quantity, absolute value of this. As this increases, the value of beta actually decreases. And we call it operating characteristics curve. And it's actually, if you decrease this one, the probability of accepting a null hypothesis will be increased, and vice versa. One more thing is actually defined. We call it a power function, or simply a power of the test, which is 1 minus beta mu1, which here is 0.6. 0.66 or more specifically 0.61. What does it mean? It is the probability of rejecting a false null hypothesis. 60% cases, a false null hypothesis will be rejected. But 40% cases, a false null hypothesis will not be rejected. This is not a good one. So what we want to do, we want to increase the value of the power function of a test. How? To increase the power function of a test, actually, only way to do it is we want to, for a given significance level, we want to improve the power of the test. That means we want to reduce the value of beta. And to reduce, the only way to reduce the value of beta is by controlling only parameter, that is n. And an equation actually exists, which is this one. So here actually, if we look at the parameters here, sigma square is the non-variance, mu naught is the false null hypothesis, mu1 is the true null hypothesis, z alpha by 2 is the z value corresponding to the significance level of the test. What is z beta? Z beta actually gives you a value of beta. So since still we are dealing with the normal distribution curve, the z beta actually tells you, z beta actually, what is the probability of type 2 error that you want to set. Let's say you want to, in the last example, we got it 0.39. Say you want to actually set it 0.21. That means only 20% cases you will accept a false null hypothesis. To do that, actually, what if you want to set this area, forgive me, it is not, is this? Okay, this one was increased. Where were I? We are here. Okay. We are here. Sorry for the interruption. And as I was mentioning, in the last example, we have a beta value which is 0.39. That means 90%, 40% cases actually we accept a false null hypothesis. We want to make it, say, 0.25 only. Then actually for 0.25, we need to find a value of the normal random variable for which this area is 0.25. We call this beta. Sorry, we call it z beta. That means it is equal to z.25. And from the normal table, what is the value for z.25? Let us have a look at it. Z.25 means to the left hand side we have 75%. So we need to find the value 0.75 right here, which is 0.68. So it is 0.68. And now, actually, we took it 0.68, they call it 67. Why? Let's see, check it again. 67 is more closer. To me, 68 is more closer. Okay, we'll take 68. Doesn't matter. Anyway, now, how many signals need to be sent so that 0.5 level of test, this one has at least 70% probability of rejection, 75% probability of rejection, or 25% probability of accepting the false null hypothesis point, mu is equal to 8. Okay, now they have changed it to 9.2 instead of 10, which we test 10 in the last case. So how can we solve the problem? The solution is very simple. We have the equation n equal to this one. Then step by step, let us find the values. First quantity is Z alpha by 2. Significance level is 0.05. If it is not given, you can assume it. Then 0.75, it will be Z 0.025, which is 1.96. So we got this value here. Fine. Then Z beta comes from the value of beta. The value of beta that we want to set beta is equal to 0.25. So Z 0.25 equals to 0.68, as we have seen from the table, but they have taken somehow 0.67. Okay, either one is okay. So 0.67, we got it. Then we have the sigma square. Sigma square is 4, as we have been continuing this one. The difference between these two, this one is 8, this one is 9.2, is equal to 1.2. So 1.2 square. And we find that 19.21 is the value of n that we need to have a value of type 2, probability of type 2 error equals to 0.25. And actually n equals to 20. If you check it other way around, that what they did here, okay, for a value of n equal to 20, what is the probability of the type 2 error? By applying this on the formula of beta, here, actually just the n has been changed. It is found that this becomes 0.23, 0.235. Actually, you can consider it 0.24. Why not it is 0.25? Because actually the calculation actually produces a value of n equal to n.21, which we actually approximate to n is equal to 20. That's why the probability of accepting a false null hypothesis becomes n equal beta equal to, instead of 0.25, it becomes 0.24. Okay. Actually, this is all about hypothesis testing. When actually you have normal population and variance is known. Any question here? The test can be one-sided. What do we mean by the term one-sided test? In case of two-sided test, this is the mu value. We consider Z alpha by 2 here minus Z alpha by 2 here. This is a two-sided test. This becomes the accepted region. In case of a one-sided test, we have two options. Z actually alpha is here. Only this is the rejection region. And this is the acceptance region. So in case of a one-sided test, actually we have two different tests possible. One is this one. And as you can understand, the other one is minus Z alpha. So this is the acceptance region. And this one is the rejection region. How we define the null hypothesis here in the first case? We define the null hypothesis Here, null hypothesis actually mu is less than equal to mu naught, and the alternate hypothesis mu is greater than mu naught. But instead of keeping this one mu naught exactly equal to this, what we do, we actually accept this one. This becomes the acceptance region. This becomes the rejection region. In case of this one, the lower part, the test becomes S naught equal to greater than equal to mu naught. And the alternate hypothesis as the rejection region will be mu is less than mu naught. And everything remains same. Just let me go to the table. You will find a table in the book. Very good one. I will just attach this table with the question. Let's check it. Can you see the table?
Yes, sir.
Okay. The summary of the hypothesis testing is given on the top of the table. What is this? We want to test the hypothesis from a sample, this one. The sample is taken from a normal population, where sigma square is known. The statistic is, sampling statistic is this one. Now, for this test, we have three options. The first one that we discussed in detail was, this is the test statistic. The null hypothesis is this one. The alternate hypothesis is this one. And we reject if this one is greater than this one or less than minus z alpha by 2. And we also have the p-value right here. This will be given in the question. This one actually is a one-sided test. Less than equal to E is the value and greater than E is the alternate hypothesis. The test statistics is same. And we reject if it is greater than, just as I draw. This is the rejection region. And actually, the 2 is removed here. And as you know, this alpha by 2 is removed here. Here we have alpha, here alpha by 2. And the third one is similar, just it is the lower test. So we call this one one-sided upper test. This one is the one-sided lower test. And throughout this table, it is a standard normal random variable. So you understand the table or not? This is very important. If you understand the table, you can solve any problem that is, if you can identify that the problem is from a normal population, if you can identify that the parameter sigma square is known, if you identify that test statistics is calculated by square x bar minus mu naught divided by sigma divided by square root of n. This square root of n is actually taken in front instead from the denominator. You know, it is same. And then the significance level alpha test, actually we reject the null hypothesis when it is in the critical region, and we can calculate the p-value. So if you have the table in place, then you can do it. Someone at the beginning answered the question that if sigma square is not given, if sigma square is not given, then actually x bar minus mu naught sigma divided by square root of n, actually we cannot apply this formula. Instead, we define the test statistic equal to x bar minus mu naught divided by s divided by square root of n. And you know, this quantity is P distributed with n minus 1 degrees of freedom. And in that case, a similar table exists in the text. Similar. Everything is fine. Just changes. Here, actually, this test statistics is calculated. Instead of using sigma, we use S. You cannot use this one, Z alpha by 2. You need to use what? T
T alpha by
T alpha by 2, comma, n minus 1, right? because the degrees of freedom will come with it, and everything else remain same. Just let us have a look. I am not actually explaining it because all the things are similar except this here. Just look at it. This one is a sample from a normal population. Mind it, the population has to be normal. Sigma square is unknown. And we need to calculate the sample mean and sample variance. We know the formulas. And in that case, if the hypothesis is mean is equal to mu naught, alternate hypothesis is mu not equal to mu naught. And actually the test statistics is same, replacing sigma by S. And here Z alpha by 2 is replaced by T alpha by 2 n minus 1 and same. So whenever you have the hypothesis testing related to the mean of normal population, the question that is, you will ask yourself, sigma square given or not given? If it is given, then the test statistics will be x bar minus mu naught divided by sigma square root of n, and the TS will be compared with Z alpha by 2. On the other hand, if sigma square is not given, the test statistics will be x bar minus mu naught S divided by square root of n. From where S will come? S will come from here. And then we will compare TS, T alpha by 2, and so on. Is this clear? So all the solutions are same. Now there is one more thing that is related to the T distribution. The T distribution curve table includes one more quantity, that is the degrees of freedom. That's why you will not be able to get the value of a T distribution random variable, T distributed random variable for all values of TS. In that case, you are allowed to what? Interpolate the value. For example, if we find that, okay, let me go there directly. This is chi-square. Chi-square is same as well. This is the T. For example, whenever you will calculate the probability, say when it is moving from 0.25 to 0.10, the value increases for a significance level, say 19. The value increases from 688 to 1.38. Right? For a significance level 19, the value increases from 0.688 to 1.328. Now, question is, if you have to calculate the value 0.78, what will you do? For the value 0.78, 78 is not here. We have 0.688, 0.113, 0.68, 0.132. And the probability is 0.25 to 0.10. So the probability will be in between here, right? Now you can find the gap here. And accordingly, you can set a value. Say for this could be say 17, 18, 16, or 15, just based on, for example, here, if you divide it into 4, 6, 8, 7, 8, 9, 6, 8, 7, 8, 9, 8, then 1.8. Okay. Then actually you can divide it into 4 or 5. And accordingly, if you divide it into 5, then actually it will decrease by 0.5 or 0.3. Then actually it will be 0.22. 0.22 or 0.21. And accordingly, actually you can calculate the value. For example, if we see an example here, very good one. Right. It says some public health officer actually claims that the mean home water use is 350 gallons per day. So minimum, mean value of the water used at a home is 350 gallons per day. To verify this claim, actually, you study 20 randomly selected homes, and actually the results are given here for 20 homes. Do the data contradict with the official's claim? You see, nowhere it is mentioned that it is a hypothesis testing problem. But you need to understand, do the data contradict the official's claim? Do the data actually is consistent with the official's claim? Do the data is inconsistent with the official's claim? Or will you reject the hypothesis? So what we need to do is, we need to identify the parameter. The parameter is mean use of water. So in a population, we assume that it is normally distributed. So, and mean is claimed to be 350. So the null hypothesis is 350. Alternate hypothesis is not equal to 350. It's a two-sided test. Unless otherwise stated, always you will go for two-sided test. And from this actually data, you calculate the expected value, sample mean, and also you calculate the sample standard deviation. Mind it is not the sample standard variance, it is sample standard deviation. Variance will be 400 or something like this. And since the variance is not given, the test statistics is x bar minus mu divided by s divided by square root of n. Then you can see it, x bar is 353.8, mu is 350. This becomes 3.8. So 3.8 is here. And square root of n equal to 20, it is here. And the standard deviation is 21.8. So this becomes 7778. Now, for a value actually 7778, when we actually calculated for a alpha equal to 10, alpha equal to 0.10, the t value is 1.73, which is greater than this one. And so we do not reject the null hypothesis. 10% level of significance. On the other hand, in calculating the p-value, what we calculate, whether this one is greater than this one, and the value, this one is not there, as I mentioned, 0.22 actually is the approximated value. So you need to approximate the value. If the exact value is not given in the table that will be available in the exam, what you need to do is to approximate the value. Okay, so that actually ends the hypothesis testing for, what time is it? 12:28. Okay, 115 minutes. Okay, let's go some minutes more. Then we'll discuss the question. So please try to understand this table. Both the two tables are same, only difference is in one table we use the value of sigma, in another table we use the value of the sample variance, and the use of sample variance actually changes the distribution of the test statistics from standard normal to t distribution with n-1 degrees of freedom. It is very common, especially in measuring the performance, testing the equality of means of two normal population. You understand what do we actually tell here? We want to mention that we want to test the equality of means. Equality of means means, say, you have two machines and you want to measure the mean value of some quantity related to these two machines. So from these two machines, you collect two different sets of data and you want to actually test whether the two machines are identical or not. That means the hypothesis is from the first set of data and from the second set of data, first set of data is taken from one population with mean value mu x and sigma square x is the variance. The second set of data is taken from another population with mean mu, and our goal is to test the hypothesis that both the two machines have the same mean value. Okay. Or the alternate hypothesis is, so what is the test statistics? Calculating the test statistics is important here. Just let me, actually this null hypothesis can also be written in this way. We want to test that the difference between the two mean value is 0. Then the sampling statistics that actually represent these two is x bar minus y bar. Now, since this one is normal, so x bar is normal with mean mu x and variance sigma x squared x by n. And y bar is also normal with mean mu y and sigma squared n. Then this quantity is the sum of two normal random variable. And as we already know, the sum of two normal random variable is also normal, with mean is sum of the mean of these two, and variance is the sum of the variance of the two random variables. So what we can write that, okay, let me write it here. X bar minus this one is also normal with mean mu x minus mu y and variance if this is the case, then actually our hypothesis testing is this one. So our test statistics, this one has a normal distribution. So we go back to the first case and we know the variance. So the first case was TS equal to x bar minus y bar minus the mu value, difference of mu, which is mu x minus mu y, divided by the variance is this one. Very interesting thing here is that when the null hypothesis is true, this is 0. So this quantity is 0 and is eliminated from the test. So our test statistics is this one, and once again we compare it with this one and minus z alpha by 2. If the test statistic is greater than this one or less than this one, we reject the null hypothesis. Otherwise, we accept the null hypothesis. Here, actually, another table is given. The table has 3 lines. I showed you the first line, this one. We have a sample x1 to xn with parameter this one, another sample this one with parameter this one, right? We have the null hypothesis, this, and alternate hypothesis, this. Now, question is, If sigma 1 and sigma 2 are known, then the test statistics is this one, as I showed you, and we reject in this case, and we calculate this one. This procedure is same as the known sigma square case for the single mean. Now, what are these two? In the third case, we have seen this one for confidence interval estimation, and we said that whenever actually sigma 1 and sigma 2 are not known, sigma 1, sigma 2 not known, but n and m are very large, in that case actually still this quantity is approximately normal. This quantity is approximately normal. Actually, when n is very large and m is very large, we actually assume that the sample variance represent the population variance and the for both the two samples. So the first case and the third case becomes identical even if sigma 1 and sigma 2 are not known, but n and m are very large, say more than 100, more than 200, more than 300. If the value of n is more than 100, then you can assume that S1 and S2 actually approximately equal to the population variance. Okay, but the middle one is a little tricky. The middle one is a little tricky. It says, if sigma 1 and sigma 2 are not known, but the assumption is they are same. Even though we do not know the value, but we assume that they are same. In that case, actually, the test statistics is this one. It will be given with the question, and it has the t distribution with n plus m minus 2 degrees of freedom. The remaining things they're saying are same. Actually, here the variance actually is given by the variance is n minus 1. Actually, okay, instead of writing this way, we prefer to write the variance is sp square one by n plus 1 by n. This is the variance where sp square is n minus 1 s square. It's not s square, actually it should be s1 square plus m minus 1 s2 square divided by n plus m minus 2. So actually this is the variance, and so like this here we divide this variance. When actually we divide it by sample, we can call it the sample variance, or actually it is called the spool variance. In that case, this the test statistics has a distribution which is t. Remaining processes are same. Any question here? Actually, the middle one. Before we leave this chapter, just one more thing. If the hypothesis testing is concerning the variance of a normal population, that means now all the tests that we have considered, one was the known variance, we test the mean. Unknown variance, we test the mean. Third one, we test the hypothesis concerning the difference equality of two different means from two different populations. Here actually we want to test the hypothesis concerning a parameter which actually is the variance. And our null hypothesis is variance is equal to given one, variance is not equal to given one, alternate hypothesis. And you know, we already know that n minus 1 into s square divided by sigma square has the chi-square distribution with n minus 1 degrees of freedom. We have used this one in case of estimating the interval for the variance. in the last chapter. So this quantity has the chi-square distribution. So our test statistics is this one with chi-square distribution, and we just compare it. The chi-square distribution has a curve like this. Here it is 0 and it goes to the positive value. So we have this point, which is chi-square alpha by 2 n minus 1, this area, and we have here one point, which is chi-square 1 minus alpha by 2 n minus 1. There is a problem. The problem is that the table that are available in many cases actually, sometimes they consider they have the value for this one 1 minus alpha by 2, sometimes they do not have. But fortunately, we will provide you a table which has, here you see, this alpha by 2 is 0.025, that means alpha is equal to 0.5. This column is here. This is alpha by 2 is 0.05, alpha is equal to 0.1, alpha by 2 this. And here you have 0.975. 1 minus alpha by 2 is 0.975, when actually alpha is equal to 0.05. So you can actually get the value for those from the table, and the table will be available. And accordingly, or similarly, we have the test here. Shall I consider an example? Okay.
Yes, sir.
Okay. A machine that automatically controls the amount of ribbon on a tape has recently been installed. This machine will be just to be effective if the standard deviation sigma. Machine that automatically controls the amount of ribbon on a tape. Okay. Something like this, say you are considering a toilet tissue roll, and the machine actually automatically measure how much tissue will be given in a roll. It is the case of a ribbon. And actually, the variance is calculated for amount of ribbon on a tape is less than okay, just a minute. This machine will be just to be effective if the standard deviation sigma of the amount of ribbon on a tape is less than 0.15. If a sample, okay, you understand? The point here is a new machine has been installed. A new machine has been installed, and the standard deviation is whether less than, that means sigma is less than 0.15 or not. This is the null hypothesis. And the alternate hypothesis is sigma is greater than 0.15. Okay. One more thing is here. What is the square root of 0.15?
Sir, we have the square 0.15.
Yes. The square of 0.15. Just a minute.
It be just less than 0.15.
0.15 square. Okay, 0.15 square is 0.0225. Okay. So since the standard deviation has been, actually the parameter is standard deviation sigma. So forget about this. Parameter is sigma, and it is given, we have sigma is less than 0.15 and less than, and sigma is greater than 0.15. But We want to test it in terms of the variance. So the null hypothesis will be the square of this. Sigma square is 0.0225 and sigma less than or equal to, and this one. What is the test statistic? The test statistic is TS equal to n minus 1 s square divided by sigma square, right? S square has a value 0.025 and n equal to 20. So 20 minus 1 is 19. S square divided by this one actually is S square is 0.25, is results in, so has a value 21.111. Now question is, at a significance level of say 0.05, whether you will accept the null hypothesis or you will not, you will reject the null hypothesis or not. How can we do it? We need to check, we need to find out two values from the chi-square. This is chi-square alpha by 2 n minus 1 and chi-square 1 minus alpha by 2 n minus 1. Okay, and alpha is, since alpha is equal to 0.05, so we will have this one equal to chi-square 0.025 n is equal to 2019, and this will be chi-square what? 1 minus 0.025 equals to what? 5. If we divide it 3, then this becomes 7, 9, right? So it will be 0.97519. So let us go to the table. One is 0.02519, one is 0.97519. Okay, here we see 0.025 is right here, and 19 is, can you see the value? The value is 32.85, right? And 0.975, it will be 8.91. What is our value? 21.11. So it is greater than 8 and it is less than 38. So we do not reject the null hypothesis. So this is one way of the test. The other way around is you can calculate the p-value. How can you calculate the p-value? You can calculate the p-value by finding the, from this chi-square distribution curve, since it's a one-sided test. Oh, I forgot, it's a one-sided test. So I do not need to go for this one. If it is less than, this value is 38. So 21 is less than 38. We do not reject the null hypothesis. And for one-sided test, the p-value is calculated just here. Actually, the value is 21.11. We need to calculate this area. Don't be confused with this term. Actually, all of them use the computer for calculating these values. You will not get these values. Why? Let's see. For 19, we want to compare this value with 21.11. Come here. 19, the value close to 21 point is actually in between 18 and 27. 18 and 27. So it is 0.5 to 0.1. 18, 27, 20, more closer to this one. So my understanding is it will be 4.2, 4.3, something like this. Oh, it is 3.3. So you need to actually, the values, For 19, the values are, closure values are, one is 18 and 27. 18 is related to 0.5, 27 is related to 1. Values are 18 and 27. This is 0.1, this is 0.5. Our value is 21. So 21 actually, so whether you will be closer to 0.1 or 0.5. Since 21, it will be closer to 0.5. So 22 would make it 0.25 or 0.3. Yes, 22 will make it, 22.5 will make it 0.3. So since it is 21, it will be closer to 0.33 or something like this. So it is not necessary that you need to find out this exact value. If you write 0.3, 0.35, 0.31, all are okay. Just you need to understand, you need to mention that the closure to values are 0.5 and 0.1. For 0.5, it is 18 and 27. Then actually, I will understand that you know the procedure. It is not necessary that you need to come up with the exact value. Okay, is it clear? The last topics of the semester. Testing the equality of variances of two normal population. We have variance from one population sigma x, another population sigma y. We want to check whether they are equal or not. Right here. And they are not equal. The question is, we measure the sample mean, we measure the sample variance, and as we know, the sample variance and this one have chi-square distribution with n-1, chi-square distribution with m-1 degrees of freedom. To compare these two, what we do actually is we divide these two. And dividing these two actually gives us a distribution known as the F distribution. First, let me write it. Chi-square distribution with n-1 degrees of freedom divided by n-1, and a chi-square distribution with m-1 degrees of freedom divided by m-1 has the F distribution with degrees of freedom equal to n-1, m-1. Now, whenever we divide